So let's wait a tiny bit until the stream is there so I can check if the audio works. Dun, dun, dun. And then we'll continue with the project. Yep, 30 seconds of latency. That's quite a lot, but it's okay. Somehow the audio is hashed, I don't know why, but it's still unintelligible. No, the audio is there and it works. Yesterday we started with my own industrial USB hub design, and we've tested the power input supplies. We have 3 different power inputs and then it selects. There's already a budge and there are already a few mistakes. But that's okay, that's a prototype. And one of them was, for example, this electrolytic cap. It doesn't fit in the case. Here. That's the case. Let's see if you fit in the case. Now I can't because they are the plugs, but it is, yeah. You see it is too high. And actually I only have, this is 20 millimeters high. And I only have 13 millimeters clearance. And for 50 volts, there are no, I didn't find any capacitors which have only less than 13 millimeter height, or at least, well, not 50 volts and not with 470 microfarad. Maybe I could use less than 470, but the other solution would be to not have it standing up. Here's the capacitor. Let's zoom a tiny bit. So not have it standing up, but the alternative is to have it lying low. And I would need to move this capacitor, a couple of traces, but I think that will be the solution. I will just have it lying low. And I've checked, actually the part I have, so this is 47, so the 47O stands for 47 millihenry. Although in the design it's recommended 33 millihenry. Don't know why. Oh, microhenry? Millihenry? I don't know. And the one I use has also J leads, so I don't know why my footprint generator generates these kind of huge pads on the side. They could be a lot smaller. I have to fix that too, or I'll look at why that's the case. So to design, I have to. This is so. This was the things which I need to fix. Up. Reduce height. No, I can't reduce the height. Lie C4 down. That's the solution. So the power input works. This is the first prototype. Let's get to the next phase, and in the next phase I wanted to check actually if the USB chip works, if USB hub itself without any power control for now works. So yeah, just input USB, is it reachable, and then output USB. So this is done. We'll start with a fresh board because we're testing a new part. This goes away and then we can start. So I can switch off this light, debug works, and we've started. Tech up. So let's use this holder, and we will start from, I think, from left to right. Actually, I'll start with the QFP. No, do I want to start with the QFP? Yeah. So here we have a QFP, a QFN chip. I have 5 of them. I only need 1. And this is the USB hub. And here we have a QFN chip. So we have several solutions how we solder it. Do I want? Yeah, I think I'll try with some paste and hot air. And then I can fix it. I can still fix it with the soldering iron, but the paste solution might be easier. I don't have any stencil. I hope the solder mask is good enough. I'll just put not a lot of paste, just tiny bit, and then I can still fix using the soldering iron if there's not enough paste. Do I want to put it now or afterwards? Let's put it now. Done is done. This is the hardest part. Most of the others can be done using the soldering iron. So I need some paste from you, syringe. This is old paste. Not ideal, but it should do the job. Yeah, it's coming out. Far too low. Just a tiny bit. It's not a lot. Center pad also. With the soldering iron, I wouldn't have been able to actually put some paste, some solder on there. At least not easily. Tiny bit. Last row. I didn't order a stencil because this is just a prototype, it's not mass production. And this is the only part which is kind of harder to solder. And I'm not that familiar with QFNs. I did solder a few of them, but not too many. I did unsolder a lot of them. We'll try out. Up this way. Some tweezers to put it back. Pin 1 is indicated. Wrong tweezers. Let's clean the tweezers so it doesn't stick. And pin 1 is indicated with a silk screen with a corner. So pin 1 is this corner here. Up. At least the footprint is correct. I did design a footprint before I had the parts. I didn't have this part in stock. So let's put it to 350, something like that. This is leaded paste, is it? Let me check. Oh no, this is unleaded paste. Yep, that's unleaded. So a bit higher temperature. And let's test. Let's heat up the whole board for now. So we at 340 degrees, should be okay for soldering. It's weird, this is a microchip chip, isn't it? But it's marked as MSC. Thought it was microchip, maybe microchip bought them? That's weird. Or maybe just remember having microchips, seeing microchips USB hubs. So yeah, now the solder paste is soaking. I see it losing its flux soon. So now it is getting warm. Let's make it warmer. Up. This is also very old solder paste. It doesn't work that well, but it will work good enough. We will have to rework no matter what, I think. That's not an issue. Come on, flow. It also has a huge ground plane, which takes a lot of heat. The board. Let me zoom so you can see a bit more if the reflow is happening. For now it is not. Do I have to put more heat? Either more heat or more airflow, but I want more airflow, so I'll put more heat. The idea is to have more energy going to the board. Yep, now it flows. But this solar paste is old. Okay. At least the alignment seems okay. Yep, alignment is right. Yeah, solar mass makes wonders. A couple of bridges. Some of them are not connected. I think we should be fine with a bit of rework and then it's done. So it's rework. Up, soldering iron, heat up, and plenty of flux. The board is very warm. I hope, yeah, I think in the middle it's also soldered correctly. Maybe not. At least there's some kind of conductivity, that's for sure. So, is this soldering iron warm? Not yet. Okay, now it's warm. Let's try. Solder. Wow. Somehow they're not easy to solder. Okay, that's one side, which seems plenty fine. Here there's not enough solder. I need a tiny bit. Let's get the thin wire. Tiny bit more solder. Just a drop. Okay. Yep. Just in one pad, which doesn't have any solder. Pretty sure it's the ground pad. Yep, they're all soldered. They all look nice. I just hope there's no shorts underneath. Looks nice. Last side. And the last pad. Come on, last pad. Yeah. Okay, it wasn't that hard. Well, I don't know if there's a short. I don't see any. We'll see in the end if it works. But now, do I want to wash it off now? Yeah. Let's clean it. And for cleaning, I'm just using this. There are two things I'm using actually. This lint-free nail polish, nail thing. But it's not actually that lint-free. Is this better than toilet paper? or tissue, but it can still leave some residues if they are sharp edges. But it works well. So yeah, this is nail remover thing. It's from a cosmetic industry, and it works quite okay. It's very cheap. Okay, this pad is not soldered. And this is, I don't know what this kind of pad is, but it is not soldered. So we need more flux again, and we'll do the same work. Where is the fine solder? Here's the fine solder. Add a tiny bit of solder, and come on. It doesn't want to solder. Okay, now it is. Okay. Check on the other sides. Yep, it looks fine. Looks fine. Looks fine. Let's clean it again. Let's wait a bit and it cools down, so we don't stress it too much. And once it's clean, it's easier to see if there are mistakes. Yeah, now this pad is soldered. Looks okay. So I did read actually on USB design guidelines, because again I didn't design the USB hub, that you shouldn't put decoupling capacitors on the back side. You should put them on the same side. Maybe, but here I really didn't have the space. I need to fan out all the traces, and if I have all these capacitors here, I can't fan out all the traces. So I did put them on the back, and I hope it will work okay. So here is the connector. We'll put it last, else it's in the way, although I could hold it this way. No, we'll put it last. Let's put the decoupling capacitors, and we have plenty of them. We have 1 and 1 microfarad and 100 nanofarads. I'll use the other solder. Yep. This one. So, what is C8? C8 is 100 nanofarads. Where are my capacitors? Here. Actually, let's use. Yeah. We need 100 nano. This is 100 nano and 1 microfarad. This is 1 micro 0603. Up. See, we need lots of them. I'll just get a bunch. Check. That should be fine for the beginning. Else we can still add. So on the right side I have 100 nano, and on the left side I have 1 micro. 1 micro, I think they're not that many, maybe 4 or 5. Let's have 5 for now. So C8 is C6. I think I don't require it. This is for the decoupling capacitor. Oh yeah, if I move this, I have to. If I lay this one down, I have to move this one, and this one. Probably a couple of traces, but so is life. So let's put some solder on the pads. Can tack on it. Up. So C8, I'll double check 100 nano. I really hope they are. So I don't think they didn't count, but there's really a lot of decoupling capacitors just for one chip. C9 is 1 micro. Up. C17, so let's cross off. Tack. C17, 100 nano. C16, 100 again. we have a resistor, which I don't care for now. So here we have C14. We have 16, 17, that's done. 1400 nano. Up. This is C21, I think. Yeah, it must be C21. C21, so that was C14, that's done. C21 is hundreds. Up. Then we have C18. And that should, no. Ooh, there is, C21 is this side. Up. Wrong one. This is C21. This is C18. C18 is 100 nano also. Damn it. Could have left it there. C19 is 100 nano, and then we have 1 micro. Nano. 1 micro. So that's 18, 19, 20. That's done. 21 I also did it. We have 12. 12 is hundreds. 13 is 1. This is a resistor. Then we have C10. Well, 12, 13 is done. C10 is 100. That's... Oops, I just lost it. Oh, here it is. I didn't know if I would try to find it because it's so small and so cheap. It's not worth the effort. C10, 100 nano. 11 is 1. 11 is just there. 11. Then 22 is 1. Oh, wow. I didn't count them, but actually I've used all the 100 nano and all the 1 micro. Okay. So now we have to solder the other side and clean the first side a tiny bit. Yep. Come on, reflow. Okay. 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 Okay, that's one side. Let's clean the other. Done. Then first side. Clean the second side. Clean the tip. No capacitors anymore. Not. So. And I'm not doing USB 3. I think that should be fine. With the decoupling capacitors on the back, the way is still very, very short, and there are plenty of decoupling capacitors. I think that's okay. Oh, it is a bit too much. Okay. And the last side. I didn't want to do actually USB 3 or USB-C, simply because most of the devices I have by far are still USB type A connectors, and I think I even disabled you. No, I didn't disable USB 3. I have one USB 3 device, two USB-C devices. One is a hard disk drive, which I use as USB 2. It's fast enough, and the other one is a software-defined radio, and that's it. So I don't care about USB 3. And for them, I will then connect. I do connect them directly to the laptop, to the computer. Okay. Oh, actually, we have one more. Yep, exactly. 1 microfarad, which is in the center. So I didn't count well. Then I need to figure out what these resistors are, and we'll check the rest of the tasks to solder. Don't tombstone on me. Okay, one side. It's not very straight, but it's good. It holds. This was C15. It's good to double check also the crossing on the page. So next is R14. What is R14? R14 is it's a config, 100K. This is to select where it boots from, because this hub can boot from either Assembers. I'm using A2C EEPROM, but there are several. Let me take something else. I don't want to have to take one resistor after another. We'll use this turntable to do our job. To be closer now. So yes, this USB hub can get the configuration from several points, and I'm using A2C EEPROM, which we'll have to solder, but it's on the other side. Yep. So this is because it is a dual-sided board, it's not very assembly friendly, and there are also a mix of through-hole components for capacitors. I mean, large capacitors are still okay priced for through holes and very robust, and also all the connectors. I mean, you want rigid connectors, so no SMD connectors, everything's through hole. And we have through hole things on both sides, which is a hell to solder, so it's really meant just for me. I'll put the design online for sure for everyone else who wants the USB hub, but I will just produce a small batch, so I'm happy with it. And if somebody wants to manufacture it, it still can. Ooh, so that was R14. And R13 is also a select. This is to pull down, this is to pull up. So we select the thing. You could connect it directly to ground or VCC, but I think in the design, no, I've added some resistors because this allows me to actually change the value. If I can remove the resistor and use the pad to put another voltage or another signal level. And this way I can kind of debug if I made a mistake. In the end, you could actually tie it to ground or VCC as far as I know. Good question. You would have to look at the datasheet. So 100 I don't have 100. Yeah, 100. Up 100K. Okay, that's clean. That's 100 on this side. This was R13. We still have a lot of them actually. R12. We have on this side, is it all? There is the programming header, but the programming header will be put last because it's a through hole part, and it will be in the way all the time. If I would solder it now, if I turn the thing, it will be in the way. So we don't put it now. Why do I still have? That's actually the voltage input. Let's do that. Let's do that now. Yeah, let's go from left to right. Left being this side. This is where USB is. We need to put the 2 transistors which block the current from backfading. Yeah, we do. This is AP40P05. It's which one is it? Yeah, I have to reprint this. This has a wrong color. Yep, I'll have to reprint that. We need at least 2. Probably need more. And I need to print 2 of them actually. So is it it's Q1, Q2? It's this one. Why this one? That's weird. Q1, Q2 for USB, but USB power is coming here. I would have expected to be near here, but it's not. Not too much of an issue. You also have the schematic. Yes, you also see the schematic, but you don't see really everything. I did move the schematic. So you have to believe me. I'll move it afterwards once I've soldered these parts. I'll move the schematic so you can see which part I'm soldering. Up. Okay, so right now I'm soldering the USB input, and actually you can almost see it. That's the USB input. And so we have Q. Oh, okay. I did it wrong. It wasn't Q1, Q2. I can leave it there. But as expected, I was surprised that it's not the right one. We need to solder Q3 and Q4, which are near the USB connector, so it does make sense. Yep, Q4. Come on. That's Q3. Damn it, it wasn't soldered correctly. And we need the pull down resistor so it lets current through, because these are p-channel MOSFETs. And by default we want the power from the USB to actually power a USB chip, because we're not testing the external power. So we need this pull down resistor, which is, so this is done, which is R4. And this is 100, again, 100K pull down resistor. R4 should be right there. Yeah. We don't need the diodes and so on. These are all the other secrets. R4. Solder this side because the other one has thermals and a ground plane. To tack it on, it's harder. Up. I like this design. I think it's by Unexpected Maker of the turntable, because it really actually lets you turn the board and solder on the right side, well, on the easier side all the time. Did it solder? Oh, these ground planes are so hard. Yep. So R4 is done. So we should have, so these transistors should be switched on, and it should let the current pass. We need ferrite beads. We need one of them. Where are my ferrite beads? It's a tiny thing. NPC. What's this? Ah, here are the ferrite beads. I need only one to have clean input power. I will not solder the capacitors for the shield. Currently, I'm not testing the shield. So that's FP1, ferrite, FP like ferrite bead, and I need also a fuse. Polyfuse. That's one side. That's the other. Clean the first one. Fuse. Up. We need up. Let's see. 0.5 amps. That's the maximum allowed by USB specification. USB 2. USB 3 increased it to 900 milliamp, and USB-C increased it even more. But for now, it's USB 2 hub, so we're limiting to 500 milliamps. Up. Okay. So we have F1, FB1 soldered. Next part is here. What is Q5? Ah, Q5 is for the switch. I don't need it. We need the resistors. The TVS diodes. I need 2 of them actually. We'll solder directly 2 of them. Blah. So one for the input USB, and I'll solder directly the other one for the output USB, which will be port 1. We will only test port 1. If port 1 works, I'm pretty confident all the other one also work, because they're copy paste. Sure, there could still be some errors, but it's unlikely. And in the end, I will find it out when I solder everything. So for now, where's the pin 1 marking? Damn it, I don't see it. Oh, it's so tiny. It is a tiny dot. Where was it? I don't see it anymore. Yeah. And it does matter. So Sam, the TVS diode ensure that you don't have over voltage on the USB pins and on the power pins. So if there's over voltage on the power pins, the Zener diodes inside this TVS chip will try to suppress them. Probably blow in the way, but at least it saved your device. And this is mainly meant for ESD protection, but it does protect more than just from ESD. So was it the right side? Oh, where's the dot? No, the dot is on the wrong side. Damn it. Okay. Tack. Yeah, soldered correctly. That's the first one. And we will put it on port 1. Oh, that's pin 1. it's not very well centered. Do I want to fix it? Nah, it's good enough. Come on, solder. Remove. Doesn't go away. Let's add some flux. So we refresh the solder and sure it flows better on the pads. Okay. Up. I'll double check with the pin 1 marking because it's tiny and it does make it is important because else it will short the input power directly. For the USB data lines, not too important. For the power input, it's important. So this is pin 1, that's okay. This is pin 1, that's okay. The two marks on the same side, that's okay. So we did solder the DD1 and we did solder the 101, 105. 105 is like 1 and then 05 because it is on input 1. So 105, that's soldered. Next is power input. This is C2, C3, and U3. And I think, yep. Where are my voltage regulators? In power, I think. VREG, power, MOSFET diodes. Is it in power? Probably in there. One. It is an XC. Yeah, 3.3 volt. It's this one. What I liked on the other chip, the terminus F or FE 2.1 or TE 2.1, is that you didn't require an external. It did embed a lot. You didn't require a clock, I think. You didn't require external LDO, and yeah, it did include a lot of things, which makes it easy to use, and that's also why it probably is used so often, because it is cheap and requires lots of less external parts. Come on. This pad is hard to solder. So this is just an LDO 3.3 volt up to 200 milliamp, but I mean it's only providing 3.3 volts to this chip and some LEDs, but we will not exceed this 200 milliamps. Yep. And I think I used 1 microfarad input and output capacitors. I'll have to check it. So this is U3, yeah, 1 microfarad input and output. Do I have some here? 1 microfarad, yep. What's happening with this tin? It's not tinning too well. Up. One side. The other side. Okay. That's the voltage input, so it's C2, C3, that's done. Probably, the crystal. So we have some, damn it. This is an SMD crystal, an SMD. I think I need to hot air it. It's not polarized, that's for sure. But yeah, I'll need to hot air it. So back to this. Up, up. Some solder paste on the pads of the crystal because it has the pads on the bottom and not on the sides. Okay. Not a lot of solder, but should be enough. Up. Oh, there is a pin 1. I think it doesn't matter. Does it? If there's a pin 1 indication, it probably does matter. Pin 1 is there. So let's heat it up. And to test if everything is fine, we'll poke it, and the surface tension should actually put it in place. Come on, start reflowing. Okay. See? When I touch it, it pulls it back into place. Oh. So it's fine. It did solder. I didn't know. I don't know if you saw it, but it's there. So normally you should use the capacitors which are rated for this crystal. I think I've used 18 microfarad crystal. Is it written on the crystal? 20 picofarad crystal. But I think I don't have 20 picofarad. I do have 18 picofarad, and I think it's good enough. one side. Oh, actually, I can put it back on the turntable. It's easier to solder since I can rotate it as I wish. Like this. That's okay. Next is, so this is done. Up, up, up. Whew, I even did that. I've used a capacitance reset line, so it is kind of stable and not too jittery. This is R14, R15. So R15 is 100K probably. Yeah. And then we need 100 nano. 100 nano goes to C24. C24, it's this one. C24. R15 is the 100K. Resistor to pull the signal up so it's not in reset, or to pull the signal down. No, up. Weird. So it's active low. Okay, that's done. That's the resistor part. Then R12, it's, oh yeah, there is a bias resistor which needs to be exactly 12K and 1%. Don't ask me why exactly this value. I think, is it one of these? It's 1%. That's 1%. This is probably 12K. Let me check. What's the name of this? App. I have 21. Don't tell me that I forgot to order them. So, film resistor, 34K, 21K. Farad bead. Did I already have some? Let me check. No, I don't have 12K. I really forgot to order them? Come on. No, it must be, something must have been happen with my card. Maybe I ordered 21K instead of 12. Maybe I did this mistake. $21, that's 34K. Yeah, it's not in my order. And I don't have it in the package here, so I did not order them. So is it really? I have 21k. Maybe I just mixed 12 and 21. Is it? Let me check the data sheet if it's really 12 that it needs. We'll find a way. USB hub. Yeah. USB hub pin description. Our bias 12k plus minus 1%. Okay. I think I don't have it. I ordered. That's not it. That's not it. That's not it. So we'll just add 10k, 1k, 1k, and I all have them in 1%. So it's not an issue. It will make kind of a bridge, but it will work. So 10k, we'll put it on top, just to have it nice, and then we'll have 1k, 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 and 1k, and it makes 3 of them, and we will just build a bridge. So we tombstone the 1k. That's the first one. That's the second one. Put some salt on top. We'll measure in the end if it's really 12k. And build the bridge, one side, the other side, a bit more solder here. That was too much heat. Okay. Let me show you how it looks like. So here we have this bridge. Let's test if it's 312k. Check. Ohms. Okay, ohms work. You should actually see also the value. Why does it measure 11k? From this one to this one should be 1k. That's okay. From this one to this one should be 0 ohm. Wow. I did pick up 0 ohm from the other bin just next to it. Luckily I measured it. That's 1k. It's not easy to place. Should I remove the top one? I think it's doable without removing it. Damn it. Okay, it looks even uglier. It looks even uglier, but I think it works. Damn it! Come on! As soon as I heat up the resistor, everything is heat up, moves. Okay, now it should be 12K. 12K. And yeah, it is 1%. Or at least my multimeter says the error is under 1%, but then I have to trust my multimeter. I think it's okay. So 12, let me write it on my sheet that I need to order 12K. Order 12K. That's done. This is R12. I don't know if I did it intentionally, that R12 is actually the 12K resistor, but it's a nice touch. Now we have VBus, which is VBus detect. Okay. So the chip detects if it is connected or not to USB. And for VBus detect we have 100 microfarad. Nanofarad, not microfarad. This is R23. R23 should be somewhere. Did I put it somewhere? Yeah, I did it. Put it. I don't know if it's a good idea to have it put it on all across the board, because it goes next to the switch mode power supply. Well, switch mode power supply to the buck regulator, but it goes using the other side. I think it's okay. And it's really just to detect. It doesn't need to be a really clean signal. It saves me some space around the USB chip, the USB hub. Then R10 is 1K. Yep. 1K? Seriously? Wow, okay. There's really a high strength. But it still limits the input. R10 is this one. R11 is probably a pull down. I have to switch to sheet so you can see what I'm doing. Up. So we are soldering these things here. That's the things we are soldering. So R11 is 100K, yeah, as expected. How 100K is, yeah. Okay, that looks clean. Does it? Yep, that looks fine. So we have C23, R10, R11, that's done. Almost everything is done. Now we actually connect the EEPROM. So my EEPROMs are in another book. In my IC book, SMD book, and where is my EEPROM? I think it's this one. Yeah. 24C16, something like that. 24C16, yeah. That's the EEPROM. And then we need pull-up resistors, and I'm probably using 4.7K. Yeah, the one I identify immediately as pull-up resistors, 4.7K. It's here. Where did I put my EEPROM? Yep. Okay, so that's the EEPROM. Did I add a decoupling capacitor to this EEPROM? Probably. Yes, I did. C25. So we have 1, 2, 3 resistors. Let's put first the decoupling capacitor. 100 nano. That should be fine for such an EEPROM. It doesn't do a lot. And then we have 4.7K here. Pull-up resistors for the IC I2C bus and for the right bit, or for the right setting. So by default it is write protected, and I need to use the header to remove the write protection. So this is the minimum required. I think we have all the parts. So this done, this done, this done. Yeah, we can solder the header. 3x3 up at times 1 times 2. I don't have 3x3, 3x2, 3x2 up. Oh. And we have to put it this way, because this way it fits in the case. Okay, it's flush. 1, 2, 3, 4, 5, 6. It is soldered. So before we try, I need to solder USB pin, USB B, USB type A. So type A, that's the one. That's robust. I like USB type A. Up, this way, this way, this way. Okay, I'll try with the shield afterwards. So there are two, so there's one capacitor and one resistor. Oh, I do it now. Let's do it now. It's, I think, 1K? Wow. Okay. So that it will be higher value. But again, I did steal it from some guidelines. I did not measure it at all. So it's 1K between shield and ground and 100 nano. So 1K is probably for the DC part, and the 100 nano is for the AC part. I'm not sure if these are good values. If you know about a document which describes a bit more without too much complication and mathematical calculus, which values are fine, you can still change them on the board. These are just, or on the schematic, it's just one value which I can desolder or resolder, or I can leave them out completely and have kind of a floating shield, which is probably also not a mistake because it should be shielded on the host side. Okay, that's done. So now we will power with 5 volts and see if, no, first we will check if there is a short. Resistance up, plus and minus, I think it's these two pins. 100K between plus and minus. That's probably some pull down or pull up resistor, so that's okay. Now I need to feed USB power and check if there is no shorts. How do I do that? Also, I didn't program the EEPROM at all. We'll have to look at the values and we'll do that on the computer afterwards. But for now, let's check if the USB is there. And probably, I wonder if there is no configuration data in the EEPROM, does it still boot in some kind of default state? I don't know. But first, let's try with some USB. Do I have a USB cable where I can... USB type B cable? No, I don't think so. I have this though. No, That's not correct. Okay, I can use this. I have kind of this thing. I will put one side of the USB cable up. This side will be here. We will have 5 volts. Up. That's V minus, and then I need V plus. Up, we're set to 5 volts. Let's limit to 100 milliamp. It shouldn't draw that much. And then the other side. Can you see the values? Yeah. Up, now it's connected. And there is no LED at all for now. I will solder the LED on the upstream ports afterwards. So let's switch on. No short. And is there some power? So now let's measure if there is some power. Let's measure if there are 5 volts and 3.3 volts. But it draws nothing? I wouldn't have expected to draw something like 1 milliamp or something like that. So, voltages. On this LDO, we have 5 volt input, 4.99, that's good enough. And on the output, we have 3.3 volts. So this thing is powered, and normally if I measure here, we also have 3.3 volts. So yeah, it is powered, and there's no short, and nothing is getting warm, so it seems okay. Let's connect it to the computer and see if the computer tells me anything. I'll show you also. Let's do it. How do we want to do it? Full screen here. Journal control. Journal control minus F. So let's check if something gets connected when I connect it to the USB. Yes. Okay. It's not enumerating. So either the chip is dead or it's just simply not configured, because I didn't write anything in the EEPROM. So if nothing is in the EEPROM, maybe it just doesn't do anything. It's completely possible. Or I just messed up my surface mount soldering. That's also completely possible. Not responding. Okay. So we'll have a look at the EEPROM values. We'll have to write them. That's the data sheet. So I'll wash my hands. Up soldering iron. We'll switch off for now. I'll wash my hands because I did solder with lead. And I don't want to lick my fingers. Up. This would be kind of an LED for indicating things. Maybe downstream, upstream facing port. Maybe this would indicate something. We don't have that for now. Up. Up. So. Okay. EEPROM interface. EEPROM. Does it try to actually? Yeah, we could test if it tries to read from the EEPROM just by looking at the oscilloscope. And if, yeah, this way we know if it actually starts. Let's do that. Let's switch on the oscilloscope. Or actually, I could switch on the other oscilloscope so you can see what's happening. Oh no, you can also see it this way. Let's remove this. How does this work with the oscilloscope? I forgot. Osci capture. What is your address here? Continuously. So I'll do that somewhere. Let me just do this quickly. Switch you there. Is this multi-dashboard, Osci capture, and then I want to refresh, auto refresh every 1 second. Start. Up 3 here. Now you can also see the oscilloscope. And let's try to figure out if it does read something on the USB when I switch it on and off. So this is off. Let's have one probe on the USB, on the I2C EEPROM interface. This. And we have here is SCA. Let's enable both channels. I don't attach a second ground, should be tied together. And here we have SCL. Up. Okay. Let's connect with this. If I switch on, this should be high. It is high. Oh, was there some traffic? Let's trigger on a falling edge on any of the channels. Okay. So we'll put it in normal. We'll switch off. Okay, that's normal. And if we switch on, we are at 5. Okay, it seems to read it. Let's try again. Off. On. Ooh, this is still very fast. Is this? Oh no. Yes, it does. So the chip seems to be soldered correctly. You see, there is some traffic. It does try to read something. So it seems that that the USB chip works. Now, I don't know if I soldered the USB lines correctly and so on, D plus D minus, but at least it does try to read the, we can even try to decode it, although, we don't need SPI, I2C, channel 1, no, channel clock is on channel 2, and SEA is on channel 1. Yeah, 1.5 volt is okay. Up. Let's try to decode and switch off, switch on, and now it should actually decode. Why don't you show me the decoded data? Decode. Yeah, 1.5 volt is okay. Plus, here. Clock is on channel 2. Okay. And this is at 1.5 volts. That's okay. So it doesn't decode what it sees now, but at the next start, we should see that it tries to read. Yep, here. Ta-da! It does show some errors, does it? Oh, there's more activity. But yeah, it did something. Up. Ooh. Okay, this was not expected. There's something wrong with the... it's just again. Because... Yeah. Stop. Run stop. And now we can have a look at the traffic. And does the chip? Yeah, the chip acknowledges. We see the green thing, so the EEPROM also works. So we need to program the EEPROM. That's actually a good sign. Now it's a good question if I did my USB correctly. But for now, it's the next task is the EEPROM. So just let me clean my screens, and we'll have a look at the EEPROM data sheet. Up this. Let's switch to the full screen EEPROM, and EEPROM.h. I don't know how yet I will program the EEPROM. Maybe I want to write some code, maybe not. Let's check. EEPROM address PID. I will assign myself. So address 0. How do I want to write it down? I know. uint 8 const uint 8 USB 2517 EEPROM. Up, it's an array. Up. This way you can see what I'm writing. Up, this we can remove. So vendor ID. So as vendor ID, we will use an ID from this list. So OpenMoko USB ID. They do provide USB IDs for your devices. We will take the next one, which is free. The next one, which is free, is probably this one. So this is the vendor ID. Yeah, this is the vendor ID. First is the least significant byte. So 0x50. 0x50 PID LSB. OpenMoko. And yeah, to get a USB ID, you just need, well, just your project, your hardware project needs to be under open source license, and then you can ask them for USB ID. PID most significant byte, I think. OpenMoko. And then we probably have the product ID. Yeah. Oh, that's the abbreviation. Let's write the complete name. So we have least significant and then most significant. Least significant will be 77 if we get the next one, but for now we will use it until we get this one allocated. We are developing. We're not distributing to anyone. So yeah, okay. Yep, that's the PID. And then as most significant byte is 061. Yep, that's the PID. DID, what is DID? It's the device ID? What is the device ID? What is DID? So, vendor, least significant, most significant, product ID, here, device ID, least significant, is set by the OM using either the assemblers or the improv. Yeah, sure. Let's put lead on it. Least significant 37. DID LSB. Bit names. 1 3. So this will be the lead DID just to figure out if it works. DID MSB. Next byte 6. Yeah. Self or bus powered. Select between self or bus powered operation. It's actually both. Either it is self powered. It depends if it's connected or not. Bus powered device consumes less. When configured as self powered device, okay. Here. Please see description on dynamic power for self bus powered function when dynamic function switching is enabled. So let's have a look at the dynamic thing. Dynamic power enable controls stability of the dynamic exchange for self powered to bus powered. We are both of them. Most likely it will be bus powered all the time, but it is possible to use it as self powered device. Is enabled to help detect the availability of a local power source by monitoring the external local power pin. Exactly. If the hub detects a change in the power source, the availability immediately disconnects and removes power from all downstream ports and disconnects the upstream port. Oh, that's nice. The hub will reattach. Okay. So, do we use this local power pin? Where is my schematic? Here's my schematic. Local power. We name it. Here, local power. Yeah, okay. So local power is high when there is power provided here, because if there's power plugged in here, this switch goes open, so it is pulled up to 5 volts. So local power goes high when it is powered. Is it how this works? Pin table. Okay, pin description. Yeah. Did we do it correctly? Probably did. I probably read it this data sheet, but let's check it again. Local power. Active suspends local power here. Detects availability. Low is not available. USB gets all the power from upstream. Exactly. High self local power source is available. So this is correct. Okay. But this doesn't tell. So let's go back to the EEPROM values. Hub EEPROM. EEPROM registers. So we just have to set that it is powered. So self bus. Please see the description. Power function with power cycle enabled. Here. Note is enabled. This bit is ignored, and the local power pin is determined. Okay, so it is ignored. So we can write anything we want. It's a bit. 8 bits. So we can use anything we want, but we will tell it is self-powered because this is how it will be used most often. So it's 1. I'll still write it. So this is the first bit. Not relevant. Superseded by this dynamic power, which is called, where is here? By dynamic. That's the first value. So next value, it is reserved. So everything which is reserved will put a 0. Reserved. Then we have high speed disable. I don't want to disable. High speed disables capability to attach and forces full speed. Okay, we don't want full speed only, so we put it to 0. Allow high speed. Indicate self-powered and not bus-powered. Okay. Then MTT enables one trajectory per port. Yes, we want one per port. We want multiple TT, so this means that every port has its own small buffer, which increases the speed. I think other chips don't support it that well. One is 1 TT per port. I don't know why you would want not 1 TT per port, but still this is an option. I'm sure there's a good reason why you wouldn't want that, but it increases the speed of the USB to have 1 TT per port. EOP disable disables end of packet generation at full speed. This permits USB hub to send a further load. Let's keep it normal. Normal. Not disabled. Current sense. Over current sense. Selects current sensing on a port by port basis. Yes. All port gang, no, and none. We do have current sensing individual port by port. We do have that. Right now it is not soldered, and maybe it will indicate an error, but we do have that. So it's 0 up. 0, 1. Current sense is equal to individual port by port. This is one of the advanced. Must only be used by bus powered configuration. Oh, I didn't know that. I think if they write it, it's just because this is the USB specification which recommends it, but nobody cares. I mean, there are so many USB hubs which don't have any current sensing and which are self-powered and not only bus-powered. But who cares? We are doing our own USB hub, which is awesome. So port power switching enables power switching on all ports simultaneously. Gang, no. On port individually, yes. We do support switching on the power port by port. This is one of the features we wanted to implement. How do you say we don't support switching? So the specifications mandates that you switch on and off should be able to switch on and off all ports. I don't. That's weird. Okay, this is done. Second register configuration by 2. OB. So dynamic. We have dynamic. is equal to dynamic auto switching capable. Yes, we are. Reserved, so it is 0. Overcurrent timer delay. Ooh, what is this for? Is it to switch off when it detects overcurrents? What is this? Give me a description. Ah, come on. Ah, there's no description in the datasheet. OC timer, overcurrent timer delay. What the we will put no delay. This is, yeah, very good datasheet. I have no idea what this means. I mean, probably I should read the USB specification. But you could add a small text indicating what it does. Compound. LOEM to indicate that the hub is part of a compound. The application. No, we're not part of a compound. I don't know what a compound USB device is. No. And then reserved. These are 3 bits. So we have 8 bits. Yeah, that's fine. Next bytes. Too many configuration bytes. So 0, this is OB. First 4 bits are reserved. And then port remarking enables selects input. No, I think I don't remap ports. Somehow I managed to route it as intended. LED mode. I'm not using the weird LED mode. So standard 1, 2, 3, 4. That's standard mode. I'm not using the USB mode. I'm using another mode which they support. Notable note that requires not availability of people. It is written somewhere else. I'm not using. I'm sure I read it in the datasheet somewhere. Okay, so some LED. Okay, these are the pins, and somewhere it indicates. Here. LED indicator. Yeah, EEPROM. Indicator LED. Maybe I even wrote it on the schematic. I only meant what it does. So normally you have green and yellow. How do you want to make? I don't know about your eyesight, but I have really difficulties between green and yellow. And the green and yellow, they should indicate if it's full speed, high speed, and bus powered, something like that. We don't use this. We use another mode. Where is the LED description? LED, here. LED functionality. USB mode, exactly. So it is described. Green LED, amber. Yeah, not yellow, but amber. The difference between green and amber is not very strong. And this indicates if it's full or high speed. We don't need to use the USB mode. I used because I don't remember what exactly it means. I think it indicates if there's power, no power, high speed or low speed. I don't remember exactly, but I wanted to use this speed indication mode where you have the 2 LEDs for the speed on one diode and then the power on the other. Yeah, that's it. That's the thing. Yeah, so I only use 1 pin with 3 state and not 2 pins. And here we see that low speed green LED is on. Yeah, and they even use red and green. Probably also use it how they do. Blue and red. Ah, red and green also didn't like. Ah, yeah, because why didn't I do red and green? Because if you add red and green, it makes a yellow color, and yellow is not very different from red. So I wanted something which is really visible, and this is why I used blue and red. And when you mix them, it makes purple. Okay, so let's go back to the EEPROM. EEPROM internal registers, and we use not the USB mode, but the other one. Here, reserve PIM LED mode. We used speed indication, so it's 01. LED mode is speed indication mode, and this way my USB hub will tell me what speed the downstream device has. And then there's 1-bit string, enable string descriptors. Yeah, why not? Does it encode it different? Well, let's enable for now. The string descriptors, we will probably add the strings. Upstream this string support, and this way we can actually write product IDs. Do I want to do it now? Yeah, let's do it. Non-removable device. Each is non-removable. They are all removable. Bit 0 is reserved, always 0, so it's 0. 0, 0. Device non-removable. We have none of them which are non-removable. They all are removable. This is probably when you have when you chain USB hubs within a switch. Then we have port disabled. We don't disable. Actually, for now, do we do it? No, we don't disable any ports. No non-removable devices. No port disable. Actually, we should support disable all the ports currently because we have nothing connected on the downstream. But I don't want to change the configuration too often. No port disabled. Because in the end, all the 7 ports will be used. Bus power. Ah, okay. None of them are not. No bus power ports disabled. All of them can be bus powered, can be controlled. Oh, no, what? That's all. Port disabled for bus powered operation. Ah, no, okay. If it's bus powered, then you can say don't use any of these things. Yeah, makes sense. It's a good option. I think there can be some configuration where this does actually affect, but we want to use all 7 ports even if it's bus powered. Switch hub. Max voltage self power in 2 milliamps. USB specification does not permit to exceed 100 milliamp. Well, then let's put 100 milliamp. So it's 50. 50. I don't know how much it draws. We could check it, but we have some kind of resistors. This max bus power. This is max self power. Max self powered. Okay. I'll put a to do. I'll check how much it draws. To do. Same here. I'll put the to do and we'll do some measurements and how much it draws when it's bus powered and self powered. To do. And actually we'll also do make a to-do or something else. String indicator. We will not enable strings for now. To-do. We want to test the USB hub. We can still fine-tune afterwards. USB max. What is this? Current. What's the difference between this and this? Max power for bus USB controller. I don't know what the difference here is. Hub controller. Max current. So this includes the hub constraint. This value includes the hub silicon along with the combined power consumption of all devices, along with the of all associates. Oh, okay. All of this. That's the same thing. This value does not include the power consumption of permanently attached peripherals. Okay. Yeah. So we'll put it 50. It's still a to-do also. Same here. We'll put at 50 for now. This is the upper limit. And these are just indication probably. I'm not sure if anyone enforces that. Power on time. The length it takes in 2 minutes from the power on. I don't have anything which indicates which requires a long power on time, and we have an LDO, and this is almost immediate, so let's just put 1. So we have 2 milliseconds power on time. 3 milliseconds, that should be fine. Yes, exactly. Language IDs and so on. I don't remember them. They're USB definitions. I have to look at. At some devices. What if I do an LS USB somewhere? I'll not show you what USB devices I have. LS USB. For example, on this one. -D, -V. Does it tell me? Yes, I have a YubiKey. Here, the language. Where is the language defined? Vendor, product configuration. The language is not defined in here. No, that's not it. There's a default value. Total descriptor, configuration of interfaces. It's not written in here. I don't remember this value. Language ID. I know I've implemented it in some code. What is this value? Let's have a look at here. I want the one for English. English, give me lang ID here. Lang ID, language English 09, but it's 2 predefined symbol. It's 2 values. It's at 10 bits. Okay, reserved. So it's probably 09. Up. Language ID high. It's a 10-bit field, not that 16-bit field. Let's put it this way. It's 09, right? Was it? I don't remember that it was 09. I think it was 0409, something like that. Let's use something else. Language ID here. Yeah, give me an example. Here, language IDs. Nice. Yeah, it's been in a nutshell. I think this describes it. Yeah, it does. There's a command get language. Yeah, exactly. Get descriptor, all language ID. Exactly. And string includes language ID. We will have English. String descriptor. I encoded in Unicode. Here you see, I remember correctly. This 04 means US and 09 means English. Is it written here? Sublanguage identifier. So it is written here. United. Yeah, United. Here. United States, United Kingdom. Let's put United States, but I don't care. So it's 0409 as I remembered it. Language ID high. US 0409. Language ID low. English. Then string length, we have 0 for now. Manufacturer string. This is a to-do. I will put my manufacturer name. But for now it is 0. To-do. Product string, for now it's also 0. To-do. Serial number. I'm not sure if I'll write a serial number. You'll probably write the data serial number, the production date. For now it's a to-do. That's a manufacturer string, serial string. I need to fill them. How many bytes are these? 31 characters, 62 bytes. And it's Unicode encoded. Byte ordering, yeah, selecting programming tools. And it's in little endian or big endian, I don't remember, but it's least significant byte first. Let's put zeros, means end of string. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 30, 31. Okay, this is half. This is the other half. here is a space missing, and there should be somewhere else a space missing too. But this is a to-do. I'll put QVoodoo on there. For now, it's to-do. Let's check if it's actually really 32. Mm. $61, and I think it's okay because there's one mistake. Should be 62, but yeah, there's one mistake here, so it is fine if I fix this one mistake, which is here. Oh, damn it. This is the manufacturer string to do. Then we have the product string to do, and the serial string, which is to do. Next one, USB electrical drive transfer, no boost. I think everything should be fine. Da-da-da. No boost. Then register boosts. It's per port. Upstream, and then we have downstream and so on. No boost. Same for these ones, no boost. We are not in an environment where we need boosting, as far as I know. Port swap. Yes, we do support. We do swap all the ports. Swap the upstream and downstream pins. Okay, we don't swap. Let me check on my schematic. I know I swapped some of them because here, downstream, these are swapped, but I think these are not swapped. D up, D plus, D minus, D plus, D minus, upstream. Upstream is not switched, but downstream they are swapped, and this has to do with my routing. I didn't want any of the pins to go through layers, so they are all on the same side, on the side where the switch is. This is why on one side they are not switched. So this one I don't need. Okay. Port swap. We swap all but the upstream. So it's 0 FE. Swap all but upstream. Remap. We don't remap anything. Reserve will be default 00. Let me read. When I have page to report how the port Whoa. Logical. All physical and logical ports, they are all mapped as they should. Physical port 2 is disabled. This is weird. Do I have to say that physical port 2 is mapped to port 2? Reserved will be default 00. Let me read again. I think 00 is fine. When remapping is not, we don't remap, so we don't have to do that. It's not disabled, but we didn't enable remap, so it should be fine. Else it will just complain. Or it will say, I have no ports. No remap. I think there's still port 7. No remap. Okay. Now, status commands. Here it is. SM. SM bus power down. Interface is active. Is the SM bus the I2C bus or is it something else? Interface power down after ACK has completed. Interface is active. Status command. I don't use this same feature. Here, SM slave. Assembler slave interface is active. USB hub will signal a USB. What is this SM? I don't understand it. I would like to put 00, but I don't understand what this thing is. SM slave interface from EEPROM, but we load it from EEPROM. So why is this configuration value there? Instead of loading from external receive a code load config cell. Here. Configuration external. This is okay. We didn't activate external process no longer available. We do use. You can do that on the fly. I thought it was at boot time already. Must be downloaded. The user-defined descriptor data must be downloaded via SM. Okay, due to internal issues. Okay. I'm not using the SM bus, so do I need to write something on there? SM bus power down. Register status command. Oh, that's already FF. So we have 128 bytes written. Ah, it's the last byte. FE. Oh, okay, we do. It seems we will have 128 bytes. Ah, let's put it to 0. Status command. Not used. I think that's it. And with that, we should have 226 bytes. $256. And now we need to program the EEPROM. How do I want to program it? Okay. I'll probably have to copy paste, but I'll just use an EEPROM programmer. But I need to hold the device and reset. Which is indeed 5.3.3 volt or ground. Let's try to use a EEPROM programmer. I think it supports I2C, I2S, does it? No, it supports SPI. Does it support I2S? Mini Pro. So, Mini Pro. Mini Pro -H. List all supported devices. Ah, okay. No device. Let me connect the device if you need it. Okay. 24C16. This is I2C EEPROM. Yes, it does support that. I'll write an I do have some EEPROMs, probably ICs here. Before I write it on the USB device, I'll write a fake one. Yep, that's one of them. I2C EEPROM. Up. Oh yeah, you're not seeing what I'm doing. Can I show it to you? Probably. That's for later. Yeah. What if I switch camera? Does it switch the camera? Yes, it does. So this is the EEPROM programmer. Yeah, you just see it in the corner. Okay. Whoop. Okay, my EEPROM programmer. Pin 1, here is pin 1. Okay, in one, let's try if you can read it. And this is an, where's the sticker for it? Here. It's an 80. 24C256. N. Yes, found. Crap. Yeah. How do I use it? Search. Get show device ID. Just read ID. Get ID. Where do I say the chip? Here, device. Specify device. Use quotes. And psych. There is no device ID. On SPI, there are devices ID. Specify memory type, optional. Yeah. Specify device, use quotes. That's what I did. Auto detect. Okay, this is for SPI. We are using I2C. And on I2C, show device information. Get ID. Let's try out. Normally they should. Okay. Yeah, it complains. There is no ID on I2C things. This is an SPI flash thing. So is there some check, presence check, query, programmer version? Who cares? It's this one. Get info. Okay, this doesn't work. Update hardware check versions. Skip device, erase, chip erase. How about just read? Oh, seems to work. Reading okay. Okay, it's empty. What if I write something to it? Is there an easy format, or do I have to compile this thing? Yeah, I'll have to compile it. That's for later. Let's copy this here. Okay, there's something wrong. Let's write some Ruby code instead. Why are you complaining? Let's run this. Ruby eprom.h. Because this is Ruby. Save as Ruby and Ruby. This is this. Replace. And documents. Let's check if we have really 256 bytes. $217. So we missed something. Is there a gap somewhere? CFD0. Yes, here, reserved. All these things are reserved. And we have again reserved here. Oh, damn it. How much is this? F5 minus +1, 39, and it's after the string. One reserved. And afterwards we have all the boosts. Here we have F9. Oh, there's a default value. Default internal. So it should actually work. Internal default EEPROM. So maybe if there is no EEPROM, it should work. But I told it to use the EEPROM. So we could use these values by default. And here we have the language. Oh, 0 is language ID. Okay. Because it's a 0 string length probably. And we have no other string descriptors. So after the boost, we have, that's boost. Reserve. And then type, file type, programming language, it's a scripting language too. Script. And normally, let's try if it actually works. This is F9. F9 puts F9 should be actually F9. Let's try if this is the case. No, it's not. So we have an issue, and we have 2 bytes missing. Are there some reserved? No. So we have 2 bytes somewhere which are missing. Let's try if it works until 13. So here this would be 13. Okay. Why is this byte 13? And here it says that it should be the language. Ah, that's the string. Okay, sorry. Wrong one. String language. This is 13. 13 works. So up until there, it's fine. So we have, let's do it another way. 2, 2, 2. Okay. Product string, manufacturing string reserved. D0 should be reserved. Let's try if this works. D0. Okay, it works until there. So this is correct. Next one is boost IO out. This is called boost up here. This is F6. F6. Yeah, F6 is not right. I think I'm missing here some bytes. Yeah, I'm missing these 2 bytes. Yep. I miscounted. Yep. And now I have 256 bytes, so that's okay. And now I have to put this as binary. We will open the file, write binary, and we simply, sorry, do file dot write. I think it's eprom dot paxi, something like this. And actually, normally in Ruby you use spaces, not these things. Seems fine. F9 FE 1 2 3 4 5 50. Yep, seems fine. So now we can try to write it on the EEPROM and check if it works. This was somewhere here. Right. Incorrect file size. I don't want to write the complete thing. Use -s to ignore. Yeah, okay. Does it read it back to figure out if it worked? Yeah, reading code. Verification, okay. And now if I read it, dump.bin, dump. And at the beginning, we should see our thing. Yes, it does work. So let's try to connect it here. What is the pinout of this device? Sure, it's very, I should have used, I do have some kind of clamp. I should have used this pinout. Just powering is okay. There is reset. Yeah, I have to hold reset. I don't remember if it's low or high. So let's have some cables. Actually, does it? Yeah, I'll just use some cables. Female, male. It just needs to match the pinout. This is 80, 25, 24C. I don't care, they all have the same pinout. I just want a data sheet. I don't care which one. Yeah. Two cuts. I have 6 pins. So ground will be brown, VCC will be red. Wrong one. I do kind of respect the colors. Does it hold? No, it doesn't. So this is pin 4. Pin 4 is pin 4 is ground. I'll not do it this way. I'll do it another way. where my head is here. Can you hold on these? Yes, you can. There's something with 6 cables, that's 4. That's too much, that's 4. Well, I have to use several cables. So, let's connect one after another. Ground. We connect it to ground here. 4. Then we have 3.3 volts. This is pin 8. Then we have right protect. Orange right protect. This is pin 7. Up. Then we have STA. So that's the data. STA is pin 5. It's this one. Next cables. We have here 2 cables. This is better for the colors. This is SCL. SCL is pin 6. And then I have reset, and I think reset. I have to read the datasheet again about the reset pin. If it's active low or high. In the datasheet, kind of show that it is active low. Here, in my thing here, the reset pin is pulled up. So pulled up means it's not on the reset. Let's check if this is the case. Pin list. Reset input is when reset is pulled up is enabled and no external circuit reset is required. Sorry. Can be reset by driving this input low. Okay, so its reset is active low. So this pin should be connected to ground. So it holds it under reset while we program it, because we will power the USB chip, the USB hub, but we don't want the USB hub to access the EEPROM, so we'll have to hold it under reset. Up. So you are also connected to ground. Okay, let's try to read it out. 80, this is just 16. Oh, okay. Right. EEPROM dot pin. Incorrect size. 16 is. Does it actually query the right size? The right thing? We'll have to use a logic analyzer maybe. Just ignore it. Let's read it out. Yes, it is there. So now the chip is programmed. I could have. No. Let's do it this way. let's get some tape which holds this together so I can replug it in if required. Up this way. Now if I connect it to USB, it should work because it is programmed. It doesn't. It doesn't enumerate. Does it read the data? So I could put a logic analyzer and check on the USB if it reads the data. That's not good. That's not good. Did I misconfigure something? We see that we did see that there's some kind of activity. Up. Let's get some logic analyzer and let's debug that. Up. Here we have ground, and we need 2 pins for data and clock. Let's use a logic analyzer and figure out what is happening. I2C, that's okay. We want some disk trace. Let's say 8. I hate that Pulse that it never remembers the settings. You always have to put them. It remembers the decoding, the channel you use, but it doesn't remember the sampling rate. I don't know why it's so unusable. So let's try if it works. Okay. Does read data. It reads plenty of data. We have everything. So others write 0, 0. Why should it write? And why are you acting? You shouldn't be acting when you are asking for address rights. Oh, maybe. Ah, yeah, wrong. This way. Okay. Right. Okay. Ah, this is because data writes, so address 0. And now you're reading the data. So you're starting at address 0 and you read. Address 50, that's our thing. You ask for read and then you read, and it starts with 50. Yeah, 51D77. So you are reading the EEPROM correctly. And you are reading the whole EEPROM. So it's not an EEPROM issue. The chip has EEPROM. Did I swap upstream plus and minus? Data plus and data minus. Theoretically, it should also be swapped, because I'm also using this connection, but I don't know why I didn't have to swap it. Let's have a look at the connections. So pin 2 is, let's have a look at the PCB board. Where's my PCB? PCB is the PCB. Okay, so this is pin 1, this is pin 2. pin 2 is noted as D minus. Is pin 2 really D minus? I've already used this. 1, 2, 2 is D minus. Yes, it is. This is correct. This is V-bus. Why isn't it not named? It should be named. Ah no, it's because it goes through the fuse before it is named. After the fuse and after the ferrite bead, it's called V-bus. Yes. Before it's not. So 2 is D minus. D minus goes here, D minus goes here, D minus upstream, DM, yes. Then it goes up directly here on pin 58, DM up. 58, is it correct? Data sheets, I don't need this one anymore. Pin table. Is the impedance wrong or something like that? Ah, come on, it's not that there is a trace. It's not that complicated, even if the impedance would be a bit wrong. And so we know the crystal also works because it reads the EEPROM. Without the crystal, it shouldn't read the EEPROM, so the crystal should be fine too. The pin out, pin table, it's probably here. 58 is D minus, 59 D plus. Let's check 59. 59 D plus. 59 goes up to here. That's D plus. That's D plus. That's D plus. USB is there. So I don't know why the USB is not working. The chip is booting. Maybe I should not do a V-bus detect, but says that it is bus powered. But it should make a difference. I could try to probe the 2 pins and see if it really goes up to here. So, multimeter. Okay, minus, does it go? Normally it should work when it beeps here. Oh, yeah, okay, this works. This works. And is there a short to it, to this one? No. No, D plus, D minus are correctly there. The clock is also correct. I don't know why it's not working. Sure, I don't have the output, all the output things, but I don't think this should matter. The reset works. The clock works. What else is there? I don't know what the 12 volts bias does. It is there. Power seems okay because we have plenty of decoupling. And it does read the EEPROM. I have no idea why it doesn't work. What else is there? So we have I2C EEPROM. These are the configuration 1, 2, 3. We know it reads from EEPROM, so that's okay. The bias, we've measured it. That's fine. V-bus detect. There could be a fault here. I don't know why. But so V reset, we know local power. This is if we override. Let's tell it to not do that, but else it's just USB. These are outputs. These are inputs, but we don't care because no, this is output. This is input. This is output. This is input. Yeah. So this is the overcurrent, and it goes low. You pull it low to say it's an overcurrent. It is pulled up by default, and since we don't pull it low, it should be fine. The LED, these are outputs. We don't use LED B. These ones, sure, for now they are floating. All of these are probably fine because it is powering up correctly and reading the EEPROM. So the only thing is VBus detect, maybe. Do I want to reprogram and say, do you are bus powered only? I can. It's somewhere around here. Okay, you're bus powered, and I'm not enabling the dynamic. Let's reprogram it. Sure, it will change nothing, but I don't know else what to do, so let's try it out. It's a programmer. It's more in my programming interface. Is it this one? Maybe here. Yeah, it's this one. Right. Okay, now it's written as bus powered. Control. No. That's not it. Now I have to test if something is shorted. I'll have to test pin by pin. If there is some short under the pads or something like that. Else I have no idea what could be wrong. Except QFN wrong soldering. So let's test this out. Bench, let's go to the bench. Up. I don't need the oscilloscope anymore. I can completely switch it off. We know I2C works fantastically. This is... I need you. Up. So... Now the clock, I didn't test if the clock was running correctly. Maybe I could. Yeah, oscilloscope. Must be running correctly. Else I wouldn't expect. Without clock, it wouldn't do any EEPROM reading. I think. I'm not sure. This is a guess. This is ground and power is enabled. So if I look at one of the pins, stop, and you are in auto mode. Or it goes sleeping. Okay, I see no clock activity. Maybe it's really low. Can't be that low. Okay, there was a... Oh, this was really brief. The clock is not polarized, is it? No, it's not. Why don't I see a clock? Uh, where is my routing? Here. No, it's not polarized. No, it's not. Do you see? When it is excited, you see... Does it go to sleep too fast? That's normal. Decode. I don't want some I to see a decode. Oh, how can I disable decode? Off. Okay. Trigger. Reads the EEPROM and then it goes to sleep. Oh, is my clock broken? I see no clock signal. Even if it's low, there should be something which is measurable. Let's try if the probe works. Yes, this does. Oh, that's the reset. There shouldn't be a lot. No, that is reset. That's the clock. Yes, the clock works. So it is pulled up. Did I not solder the clock correctly? That might be the case. Ah, there was a tiny bit right there. Yeah. Going from 1.5 volt to 0. Yes, there is something. But that's not a clock. Okay. Maybe the clock is wrong and it's still able to read EEPROM although there's no clock. Let's check. We will also unsolder the clock. No, I don't think it's because I put 18 picofarads and it requires 20. I don't think that makes a difference. Let's unsolder the clock and see if it can read EEPROM. Put you here. You go here. Up, heating gun. I hope I don't break my beautiful tower. Maybe it uses an internal oscillator first to read the EEPROM, and once this is done, then it starts the clock for having a precise timer for USB calculation. For USB timing. That could be the case. Don't want to destroy my clock tower, my small tower, 12K tower. Something is heating up. Capacitors are moving. Yep. It's not a clock, it's a crystal. Because clock generates a signal, this one just responds. Seems to be soldered correctly, but let's try and figure out if it still reads EEPROM. If it's still able to read EEPROM, means it doesn't require the clock to read EEPROM, and the clock might be faulty. That's the clock signal. Oh, it was switched on. But it wasn't connected. USB here. Yes, it can read the EEPROM without a clock. So the clock might be damaged. Oh, not soldered correctly. Let me read the clock again. Is it a 24 megahertz clock that it's required? Crystal clock in. I can inject a clock actually if I want to. For now, let's have a look at the crystal. What type of crystal does it need? Well, USB hub, crystal, onboard. Oh, onboard 24 click clock crystal driver. There is an onboard one. Or external. I think the onboard one is not very reliable, but if at least it would work, that would be nice. And it has problem, maybe it has maybe issues. The one I've ordered, it was this is the clock. Let's have a look at the data sheet for this one. This is the one I used, and it's 24 megahertz, sure. Is my pinout correct, or did I mix up the pinout? This is the top view. This is the top view, so we don't care. This is the bottom view. Okay, so pin 1 is on top. 1, 2, 3, 4. 1, 2, 3, 4. Did I did it correctly? Where is my here? 1, 2. One. Okay, this is 1, but 1, 2, 3, 4. And 1 is X1. 1 and 3, 2 and 4 are ground. They are grounded, yes. 1 and 3 are the clock signals, and we see that the clock is going there. 1 and 3 clock signals, 2 and 4 are grounded. So I did this layout correctly. I'm checking because I didn't use this clock previously. It's a new part, so it's not been tested by me. You're not seeing what I'm doing. Full screen here. That's the clock I'm using. And yes, 1 and 3 are the signals, 2 and 4 are ground, and they are opposite. And in my thing, you see 1 and 3 are the signals, and you see the clock is going there. 2 and 4 are grounded. Here we have one thermal, and here we have another. Here we see it better. Here we have one thermal, here we have another one, and they are both grounded. We have even ground pin here, so they are grounded. Are they on the right pins? 60 and 61. Pin table. Let's show me the figure. 60 and 61. This is correct. We can try if there is 1.8. Yeah, there must be 1.8 volts. VDD1. We could measure 1.8 volts here to see if the internal LDO works. Pin 25. Wow. Let's check if pin 25. I need some ground here, and 25 is. Why is pin 1? Pin 1? 25 is somewhere around here. This is enabled or disabled? That's enabled. This should be 1.8 volts, and it is 1.8 volts. So this works. So the internal LDO for the internal core works, and it's also able to read the I2C, so that shouldn't be too much of a surprise. Let's put back. Where is it? That's the one I'm using. Where did I put this thing? Maybe I just have to redo it. Home automation. Measure. Okay. So, what's about the internal clock? There was something about the internal clock. Does it start the internal clock if it doesn't find anything? No, that's the overcurrents. That's the PLL. That's okay. So the clock. High speed select clock in X crystal input external clock out. Okay. This pin connects to either one of the terminal of the crystal. This is what we did, or to an external. One crystal is not used. Yes. This is the other terminal. It can be encrypted when an external. Yeah, I could provide 24 megahertz. Do I have something which generates 24 megahertz? I'm not sure. But it says there's an internal 24 megahertz. How? Here, is it just the internal 24 megahertz for? So that's the external one. There's a PLL. which boosts it so it can use it. But at the beginning, it says onboard 24. Crystal driver. Okay. Resonator. Okay. It's a crystal driver. So it does require the crystal. But we've seen that it can read the EEPROM without the crystal. Let's try again. Yes, it does read the EEPROM without the crystal. So there seems to be an issue with the crystal. Or maybe, well, that's my guess for now. How do I test if a crystal is working or not? It's a good question. I have no idea. Try to resolder it on with some new paste. Just clean it and I hope it works. Else I have no idea. Can I see if it starts driving it? Is this something you can see? Not that familiar with debugging crystals. Generally, you just use them and they work out of the box. Switch the camera back to the bench. Up. Bench camera. Bench. So first let's clean the pad before we resolder the oscillator again. Oh. I should switch off the device before I do anything. Oops. Okay, this is cleaned up. Let's clean up the crystal. Let's put a tiny bit of solder paste on there again. Let's reflow it again. That's a lot of solder. And there's no, this part is asymmetric, although we can still put pin 1 on pin 1. Just there. Okay, that's all right. And there's far too much flux. Too much solder paste. that's soldered correctly. There should be no issue with that. Let's use a second probe. Let's try again to see if there is some kind of activity on these things. Probably not, because it's requiring 20 picofarad and I'm just using 80 picofarad. Aha. That's EEPROM still works, means the chip is not dead yet. Ah, he tries to drive the clock. We see it. So it tries to do something. But that's not a clock. Oh. It does try to drive the clock. We see it here, and then it's, for an unknown reason, maybe it doesn't manage to drive the clock and then it stops. How high are clock signals actually? I'll need to use a dev board to check that. Let's take a dev board and see if I can see clock signals and how they look like. This is ground. I need some USB. This is micro USB, and I should see a clock signal. Okay. Are clocks really that low? Is this microcontroller? It's not blinking, so I don't know what it's doing. If it's running something or if it's sleeping. Don't I have one which has some kind of code inside? Nice. Any of them? Maybe I loaded too much with my... Don't know. How a clock looks like. Is this sleeping? Come on. The code I write is going to sleep normally, so is I have something which doesn't go to sleep. That. So here we have an Arduino, and I'm trying to find out if I can grab a pin. I need a ground. Let's switch on. Ground. Oh, here we see a clear clock signal. Okay. Oh, it's not this one. Yeah, the one I was using was going to sleep all the time, or using the internal. Yeah, there we see something. Sure, it's not high. And I think it's only 8 megahertz. But there we have a clock signal. And if I ask it to measure clock 2 counter, go on channel 2. Should measure something around 8 megahertz? 16 megahertz. Okay, so it should look like this when the clock is started. Yeah, I need to power this on. Back on. So let's put this back on, and oh, you're actually not seeing my oscilloscope. Sorry. I didn't see that. Osci capture and refresh every second start. Ah, and I need to start the capture. Okay, now the capturing should work. Yeah. So if I switch on, there was a brief activity, but then it stopped. Damn it, why are you not oscillating? What did I do wrong? Is this a broken clock? I don't know how to test a crystal. But at least both bits are connected correctly because it goes high. At least on the microcontroller side, on the USB hub side. No, this one doesn't go high. Do I have to tell it? Please use this. It's not the clock source, but as a crystal. Because here, on this one, there's nothing. On this one, there is. This one, there's no signal. Do I have to? I think by default it's trying to drive. Maybe no. There should be crystal driver. Let's have a look at the driver. If we need to do something with the crystal driver. Driver. Okay, it says nothing. And the application datasheet also liquid crystal display. Yeah, okay, that's crystal, but it doesn't need anything. Crystal input 24 crystal or external clock input. Pin 60 is driving it. Do I need to do something there? Yeah. Reset now. The external crystal is halted. A valid hardware reset is defined. Okay. Okay, this is just a reset, how it does that. Crystal oscillator. Yeah, I don't have this 1 mega ohm, but or else 24 megahertz. Can I generate a 24 megahertz signal? Can I have other 24 megahertz clocks? I think maybe. Typical application circuit. Well, the 1 mega ohm is so high, it doesn't make really difference. But do I have other clocks in MCU? I think I have other clocks. 8 megahertz. What is this? 16 megahertz. These are microcontrollers, these are not clocks. I don't have any 24 megahertz clock. I don't know how to test clocks and if this is broken or how do you excite a crystal? I've never had an issue with crystals. If they're internally connected, let's try to check if the footprint is actually okay, if they're internally connected or not. So let's get one of the clocks. That's a USB-D connection. Where are my clocks? Here, 24 megahertz. Let's open another one and test if it is true that pin 1 and 3 are ground. So they should be connected, no, 2 and 4 are ground. They should be connected internally. So if we take this clock here and if we measure, I need my leads which are tangled. Up. If I measure the resistance, it should say so 2 and 4. Yeah, they're connected. They're probably even connected to the shell. And actually, if I well, here they are connected no matter what. I don't know. Let's try to change the clock. Maybe I got a faulty broken clock. I've never had that, but who knows? Let's just check and see if it works with a new one. What if I turn it around? No, it doesn't. It's just a crystal. There's no orientation. I have something which generates 10 megahertz, but nothing which generates 24. I could do something, but it takes time. Maybe the capacitors are wrong. Let's try that out. Let's first. So now I changed the clock. I want a long USB cable so I can actually test and see on my journal if it works. Let's connect this to the computer. This way I can test directly if it works on the computer. Up, 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 up. And the video is gone. Yeah, I have to restart OBS. See you soon. Okay, so here we have the journal. This way we can see if when we connect, if it does something. Oh! No, that was 7 port, this is something else. We lost the camera again, don't we? Didn't we? Yes. I hate this hub. I really hate this hub. Come on. Oh. I don't know what I did, but it is working now. see. Let's check this out. Up. Now I disconnected it, but it didn't tell that I disconnected it. If I connect it, it also doesn't tell that it is connected. Does this work? Yeah, this works. There's something going on with the hub now. With the USB. It did work. I really swear it did work. What is happening with USB now? Is this hub dead? Is this port dead? Okay. This one doesn't respond anymore. Oh, the journal controller has issues. Okay, this one does respond. So this port has issues. See? USB doesn't work. I have no idea why. No. On this port, it doesn't work. Come on. This is too far away. But it did work. So let's try again to connect this up to this USB port. It did work once. Let me show you why I said it did work once. Where's the control? Here it had issues, and here new USB found. You see, this is OpenMoco. This is the one we used. This is the device. So it did work once. Why doesn't it again? Okay, my USB is broken. It's not about the crystal, it's my USB traces. They're close to each other, they're coupled. There's a impedance. The traces are going directly, there's no switching in between them. It did work once, why don't you work? I have a result. You worked. I don't know why it doesn't work now. I'll copy the one where it worked, so I have proof that it did work once. Where is it? Here. Yeah, 7 ports detected. Uptime to power cycle. It failed twice. So, does it have to do? Maybe I'll try to change the capacitors, but does it make really a difference between 18 and 20 picofarad? I can try to salvage, no, 20 picofarad. I have no idea where I could salvage 20 picofarad. Let me save this. This worked once. I'll change the capacitor, I think. And I'll try to use 18 picofarads again, but no. Let's try last time if it works. Maybe it's really my USB which routing which is shitty. Come on, they are just traces. It's USB 2. It's nothing major in here. Can't be that bad. To power cycle doesn't work. Well, let me change the capacitors. If this doesn't work, then I'll take a pause. I don't know. What could be the cause? But if it worked once with these capacitors, I think there's something, there's another problem somewhere. Okay, so this is a debug board. I don't need it. Capacitors. 18 picofarad. I do have a capacitor book. I think. Yes, I do have. Maybe I do have the right values in my capacitor. So we have inductors on this side, capacitors on this side. Let's check if I have 20. These are huge capacitors. Ugh. There's even one which is going haywire. Up. Let's put some tape. These are weird capacitors. I found them somewhere. Okay. Oh, I don't have capacitors. These are just inductors. Okay, the capacitors I have are only large capacitors. They're not small ones. Okay, I don't have small capacitors. So let's try again with an 18. No idea why it shouldn't work. I will order 20 just to be sure next time. Well, maybe I have 20. Let's check. I still have some small remainings from other project. 1 micro, 10 micro, 18 pico, 10 pico, 33 pico. What are these ones? What is this? 1 micro. What's this? 100 nano. No, 18 is the closest I have, but 18 is so close to 20. I don't know. So we have the 21s. Well, I will order 20 picofarads, that's for sure. This, I thought I did, but there's lots of parts which I didn't order. Like the 12K 1%. Where's the other quartz? I don't want to lose it. Here. Because it might still be good and I still can try to salvage it. They're not that cheap compared to the huge ones. Okay, Let's solder it correctly again. Else, I'll try to figure out how I generate 24 megahertz signal. And if I can generate 24 megahertz signal and inject it, then I know that this is not a clock issue, but some USB issue. So let's try it out. And then I'll switch to another topic. No, doesn't work. Oh, it did. If I bend it. Here. Insufficient power available to lose all downstream ports. Ah, okay. Yeah, that's not an issue. Insufficient power to yeah. That I need to fix, but why does it work now? I just bent the board. Does it work? Doesn't work? There's something going wrong. Now it works. Now it doesn't work anymore. Is this a USB trace issue, or is something not soldered correctly? And it should never take so long. Maybe I really fucked up the impedance. I didn't do any calculation. I just do thin traces which are closely coupled and with a ground plane behind. Is that how you do it? Okay, it's not a USB issue because it's probably just a soldering issue. Because when you... If it would be an impedance issue, it would never find it. Because I can't change the impedance just by bending a tiny bit the board. Okay, now it finds it. And now it's disconnected. That's maybe a soldering issue. Let me try to resolder all the points. All the pins on. We'll add some fresh solder also, just to be sure. Maybe it really has to do something with 20 picofarad. It's because it's touching them that I change slightly the capacitance and then it works. So I've redone all the pins and they really look nice, so that not it. Let's see if it's more stable now. Same. What if I touch the capacitors? Yes, it has something to do with the capacitors. They really need 20 picofarad. Here I'm not... let me switch the camera so I can show you what I mean. Up, up. And why don't you find the other camera now? Hello? Camera? Okay. So let's remove this. So when I plug this in, see, it doesn't find it. Now, if I hold my finger on where the pins are, on where the oscillator is, okay, let's try again. It did work once. See, it works. Because I'm touching the capacitors, and I'm adding a tiny bit. Let's just probe the capacitors. Come on, it worked once. Well, I'll try, yeah. I'll try to find a clock generator and inject 24 megahertz. I know I have some one somewhere, I just never used it. And if this works, we know it's because of the clock and not because of the USB. But that's not for today. I need to do something else, and I've spent already too much time here. 4 hours, 4 hours. Okay, for now it's good. But the proof of concept is there. EEPROM works, USB kind of works. The clock maybe has an issue. Power works, so the routing is quite okay. Probably tomorrow or one day I'll see how I come forward with the clock injector and if I can salvage some picofarads and so on. And maybe we can test one of the downstream ports afterwards. But for now, that's it. And we'll see. There will be a next part for this USB industrial hub. Enjoy the rest of the day.